Okay, we figured out how to calculate a couple of derivative functions. Let's see how they can help us out. Let's say I wanted to find the derivative of the square root of x at x equals 5, or maybe because I wanted to know the slope of the tangent line or an instantaneous rate of change. Well, now that I know this derivative, this flies by. Ready? If f of x is equal to the square root of x, well, I know what the derivative is. It's 1 over 2 root x. And so if I want to know what the derivative is at 5, I just plug in. Boom. 1 over 2 root 5. That's it. That's the joy of functions, is you can just plug in much faster than using that whole definition with a limit. And we will slowly learn functions that let us not use that limit definition. You still have to remember that, though, and how to use it. Just a quick note, you could rationalize this denominator. I could multiply top and bottom by square root of 5 to get the square root of 5 over 10. A little nicer. I often will not take the time to do that. Great. Let's go ahead and look at another way. We could think of this as a function. Functions have graphs. And so we could go ahead and make a graph for the derivative. So this function on the left is f, and we can ask ourselves, what does f prime look like? I'll go ahead and label a couple of points here. Make this a 1, 2, 3, 4, 5. Okay, and this is going to be f prime, and this will be x. Okay. This, for some reason, is really tricky for people. I'm going to walk through doing it myself. You should walk through it on your own several times because watching me is not enough. But this is important. I could ask myself, where is f prime going to be 0? Let's find some nice points. So f prime is 0 when the tangent line has a slope of 0, which is where that tangent line is horizontal. So like right there, right at the top of that peak, that tangent line should be horizontal, or the bottom of this trough, or the bottom of this trough. So each of those horizontal tangent lines has a slope of 0. So when I go to graph f prime, it looks like I'm going to have a 0 right here, and maybe a 0 right about here, and another one right about here. They should actually be on the x-axis. So I've already graphed 3 lovely points in f prime. Okay, maybe I can figure out where I'm going to be positive or negative. So let's just focus right now on this area where x is kind of bigger than 5. This whole area over here, my tangent lines maybe look like this and like this and like this. Those tangent lines are getting steeper and steeper with a positive slope. So if the slope is positive, that means this thing is going to be above 0, above the x-axis, and getting bigger and bigger and bigger. So I don't know a whole lot about it right now, just eyeballing it. But as this gets steeper, then this gets higher. Okay, next up, maybe let's look at this other left-hand side. As this gets from left to right, this function is decreasing. It's going down. Those tangent lines have a negative slope. And it looks like the further left I go, the more negative they are. So as they get steeper, as they go to the left, this should be going lower and lower and lower. So decreasing means below the x-axis. Okay. That's a nice place to start. Make sure you understand that. Now, what happens in between these two? Well, I'm increasing. Those slopes are going to be positive. It kind of looks like maybe the steepest I'm going to be is right here. So maybe it's going to max out, I don't know, right around here. If I did that right. And so it's going to kind of peak up and come down. And then it's going to be decreasing after that. And maybe it's the steepest right around there. So it's going to sort of bottom out right here. Okay. But notice this whole area here, I'm negative. This whole area here, I'm decreasing. Okay. And as I get closer to 0 here, it means I'm closer and closer to being flat. All right, so not a bad sketch for what's going on. It's clearly not exactly right, but it's pretty close. And you should be able to go both from the blue to the green and kind of from the green back to the blue as well. And watching me only gets you so far. You really have to think through this for yourself. So give it a try a couple of times. Okay, one more thing on this quick segment. Well, two more things. You really do need to try this several times. For whatever reason, it takes a while to sink in. It's like a new way for your brain to think. So please do think lots about it. And before moving on, I got to show you a little bit of notation. We've already seen that the derivative can be written as f prime. But sometimes if we're using y, like y is a function of x, we'll write y prime. That's pretty common. There's another kind of notation called Leibniz notation, where if we want to really be clear about y is a function of x, or the derivative with respect to x, we'll write it like this. This is important if there's a lot of different variables flying around, or even, like different constants flying around. We want to be really clear. And similarly, we could write df dx. Okay, finally, you've also seen that we can do things like this. dx of a function. If I write the derivative of a function, well, it kind of makes sense that these two things should both be there. Dx of f, all I'm really doing is basically multiplying these. I'm not literally multiplying these, but this guy Leibniz thought a lot about what would be good notation for this. And so it's meant to sort of look like exactly what you're doing. Okay, so don't be shocked if you see any of these notations in the homework or in tests or when people are writing really important scientific notes to you.